All right, we're live. Good to have other people on the call this time. For those that saw the VIX stream, fun to have a whole discussion here. So, as folks know, yesterday the Durango proposed upgrade to the Avalanche network activated on Fuji at 11 a.m. Eastern time. There were a few folks that forgot to upgrade by the activation time. So as a quick reminder, like you should update before the activation time, not after the activation time. Some people think like, oh, the time hits, now it's time to update. And so we've tried to be really clear about like the usage of the activation time. You should update beforehand to ensure you don't have any downtime. If you don't update before the activation time, when the activation time hits, your node will be disconnected from the rest of the network. Like all the other peers will drop you that upgraded. And then you'll have to use a special configuration flag to like actually reconnect to the network and process blocks that were accepted when you were disconnected. So as a reminder for folks that are new to the mandatory upgrade process and everything like that, when there's an upgrade activation time, please upgrade ahead of that if you don't want to see any downtime. Now, if you want to wait for some reason, more power to you. Hopefully the node should reconnect at that point, but it would be highly not recommended to go that way. But with that, it was a successful activation. We haven't seen any regressions yet. And this was a pretty large upgrade. I don't know if we have an estimate on like lines of code that were changed here, but a lot is the way I would say it. This has been, a lot of these tasks have been the culmination of, year plus of like digging around and getting into stuff. So it's really cool for, the entire community to see all this stuff go live. Now, another clarification, people have asked, what is a proposed upgrade? Why is it proposed? So as a reminder, like is the case on many other networks, upgrades on mainnet occur when a large percentage of stake upgrade their nodes to new software with a coordinated activation time. That's the mechanism for actually activating changes on the network. So if that happens, changes will be activated. And so we, Ava Labs or Avalanche Foundation or anyone, can't force anybody to update their nodes. We don't control the upgrade process, which is why there needs to be a collection of, a unified feel on like where the network should go. And so if enough people don't upgrade the network, what will happen is the chain will stop. Which is something that would be suboptimal. So like hopefully, upgrades are attempted by the community only when there's like very strong support in favor, which is why a quick shout out to Snope here actually put together a dashboard to track signaling progress of different ACPs. So you can go check that out if you want to. And then if you run a validator and you feel strongly in support of the things that were introduced inside of the Durango upgrade on Fuji, it's ACP 23, 24, 25, 30, 31, 41, 62. You can configure, your validator prior to the release of the code to support or signal those things. So it's been really cool to actually see a dashboard now created. Most people are abstaining so far. So if you want to support anything and help make it clear that the network is in favor of an upgrade, that'd be great. So with that, anything you guys want to talk about before we get into what is in Durango? It's our first call, I think, since actually the release of this blog.
I'm excited to just dive into Durango. It's been, as you mentioned, an extremely long time coming. So the kind of popular thing is definitely going to be the warp messaging on the EVM, but there's also just a huge number of other various upgrades scattered throughout. So I think we dive in. Do we want to start with the EVM messaging? I think that's.
Well, if we start with that, then everyone's going to toot out the rest. So I feel like we got to start with the other ones, and then we'll transition into Aaron and Michael when we talk about that one. I think let's keep it in kind of categories, maybe. Like we'll talk about subnet management first. So let's first cover P-chain transfers.
Yeah, so there's a ton of upgrades to the P-chain in here. So one of the kind of major issues that people, or not issues, but like pain points that people have run into, is that they can't actually transfer funds on the P chain. So this has led to some really weird behaviors where people will kind of abuse either export import transactions, kind of like try to like change who has funds on the P chain, or things like that. And when you see like people needing to do like workarounds that end up causing more load on the network than if you just implemented it natively, it's kind of like, okay, like maybe that design wasn't ideal. So originally we didn't really want people to be doing transfers on the P chain because we didn't want the load on the P chain. But if instead you're simulating transfers on the P chain by doing more work on the P chain than just a simple transfer, then something clearly didn't work out right in the planning. So I don't remember who proposed this. Was it Druba? Yeah, Druba proposed that we include just the simple transfer transaction to the P chain, and so this is very simple change to do because this is actually kind of the core of all the other transaction types already. So it's just basically enabling itself to be issued directly. And so I think that this will be great for kind of simplifying that UX. So who knows? Maybe we'll see a P chain faucet come out of this eventually. But who knows?
Yeah, Druba, the ACP machine, top of our list right now. Yeah, the other thing that we tackled that really helps with on the subnet management side is this ACP 31, which is subnet ownership transfers.
Yeah, I could keep talking. So the subnet ownership stuff
That
is
was my
again
smooth transition into that.
yeah. So the subnet owner tracking. It's a kind of a core tenet of security that keys should be frequently rotated, and it was really just an oversight, I would say, at the beginning of the network that the subnet auth key was not rotatable. And so like you could not actually change who was participating in the ownership of the subnet. And so Druba again proposed introducing a transaction type to essentially rotate this subnet ownership. So what it kind of does in the back end is it kind of consumes the prior owners and then produces its own generic new set of owners, which is defined using a I guess what would be called like a multi-signature requirement. So there's some threshold of participants and the keys. So
yeah, this was a big thing for people trying to get their subnets off the ground, and then later on being like, "Hey, I really wish the thing we used to control which validators are in the subnet was, I don't know, like a 3 of 5 or like a 5 of 7 or like a 7 of 10 or something like that." And so what it meant happened was usually you like went above the security threshold you hoped for at the beginning. So like instead of a 1 of 1, you did like a 2 of 3. And then usually when things started working out, you undershot your security and couldn't increase it from there. So it was just suboptimal. And the other thing too is a lot of institutions that are, considering and playing around with subnets naturally as part of security policy want to rotate their keys that they're using every few months. So this also enables you to just rotate a signer set entirely, or like if you have people join your company or leave your company, you don't have to worry about like trying to get some ledger from them or something like that. So this is a big improvement change for what we'll call like the permissioned subnet experience, in my opinion.
Mm-hmm.
The one thing that someone brought up, which I thought was kind of nuts and I hadn't thought about at all, is that you can sell the ownership of a permission subnet off chain and transfer like a subnet sign like authentication to somebody else, which was interesting to consider. I'll leave it there. Yeah, and then the other one, so I think that's the case for most of the subnet related improvements. I guess maybe we'll wrap ACP 24 into that conversation too. So the Shanghai EIPs, maybe Aaron, you want to take that just because that touches both the C chain and the subnet EVM?
Sure. Yeah, so we decided for the ACP process, at least for now, to only make these ACPs when they're related to the chains that are on the primary network, simply because since Avalanche is VM agnostic network, we didn't want to necessarily directly involve subnet EVM and any other VM in that exact same process, since people might be maintaining their own VMs. But of course, when we applied these changes, we applied them to subnet EVM as well, since we're maintaining that sort of on behalf of the whole network. But just to be clear, ACP 24 is for C chain, and we also applied the same changes to subnet EVM as well. So this was just taking the upgrades from the Shanghai upgrade on Ethereum mainnet and then applying them to the C chain in order to maintain compatibility. So that's EIP 3651 to warm the Coinbase in the access list, EIP 3855 to add the push zero instruction. This is really the most important one because as of Solidity greater than V08.20, it includes this push zero instruction, which might show up as soon as in the constructor of the contract, which would mean that if you compiled a contract using the latest version of Solidity, that contract may not actually work directly on Avalanche, and it might not even be able to be deployed. Actually, kind of the ideal situation is that it fails on deployment as opposed to failing at some later point in time. Solidity actually, since they realized that the EVM is used in lots of different places, does allow you to target different network upgrades or sets of network upgrades. So you could actually use a version of Solidity greater than V0.8.20 and target prior to the Shanghai upgrade. But nevertheless, including the push zero instruction and these other opcodes makes it so that Solidity will work out of the box with Avalanche as we obviously want. And then we have EIP 3860 to limit and meter init code. So this reduces the maximum size of the initialization code in order to create a contract. And finally, we have EIP 6049 to deprecate self-destruct. So to be 100% clear, this doesn't actually remove the self-destruct opcode, which is what we want to do in the future. And Ethereum mainnet has scheduled to do that in the future as well. It just sort of marks it as deprecated so that anybody that currently relies on it knows that they ought to figure out some migration path to stop relying on it in the future. And so that goes for the Avalanche C chain as of this EIP or ACP to activate Shanghai, and then also for subnet EVM as well. So as always, the motivation for bringing these updates over from Ethereum mainnet is to maintain compatibility as well as possible. There is also one other EIP that was included in Shanghai in order to modify the way that withdrawals are handled. That doesn't apply to Avalanche in the same way, so we didn't include that here. And the reason that doesn't apply to Avalanche is just that we don't have the same execution consensus client separation or the same mechanisms that go on within Ethereum's consensus client to handle withdrawals in the same way, since that takes place for us on the Avalanche P chain instead.
Cool. Yeah, I think one big question we get is like, how does like the Avalanche EVM try to stay consistent with or not with like other EVMs? So like I think this will become a really big thing, I think, as like you continue to see this like spread of different EVM deployments. But I think for what really matters to us is a lot of like the Solidity compiler compatibility, because that's really what people use to deploy programs or like smart contracts. And trying to support as much of that as that makes sense so that you don't have to like mod the compiler or like use specific versions like that. That kind of sucks. But beyond that, I think that there are definitely deeper tweaks. I think one mistake that was made very early on in the code base was trying to add functionality through like the addition of opcodes. That was quickly rolled back and never considered again. And now we use precompiles to extend usage, and that's definitely the recommended path, I think, across the ecosystem now. But some people had asked, like, is blob transaction something you want to support? Well, actually, on the subnet EVM, you could mod it and actually add blob like transaction support if you wanted to. But I don't think something like that, like this is the nuance of like what makes sense to have on the C chain versus subnet EVM versus anything at all within an EVM on Avalanche. And so I think there's a broader conversation to have there, but generally speaking, this is like kind of the nuance and where it's a great opportunity to chime in on the ACPs. So we try to support anything that fits within the Solidity compiler, and anything else, I think it's a longer conversation. Next, I think we go into P-chain optimizations. So I think that's remove pending stakers and disable the add validator, add delegator TX. So maybe we'll do the remove pending stakers first.
Yeah, so the remove pending stakers, I think that there was a question that came up during the discussions of this ACP. And basically it was like, why did this exist in the first place? And that is a very fair question. So the original staking design, specifically the reward kind of mechanism, was very different. And so there was various kind of different mechanisms as part of the staking design. And it required kind of a much more rigid and, to be honest, complex structuring, which is why we had things like the advanced time TX. We had things like start time, end times hard coded on stakers, and it's why we had like the pending validator set. Um, we've The network has kind of gone away from that much more complex staking design, and so now all that really matters is you're specifying kind of your duration, and then the rewards are calculated based off of the remaining supply to be minted. So there's a lot of complexity that was kind of not needed anymore. And specifically, the pending staker set was a large amount of complexity because of how it interacted with the maximum weight cap on a validator. So when a delegator is being added to a validator, you have to actually make sure that it does not breach the like maximum weight for the validator, which ends up being incredibly complex. So there were, in the very early days, actually a couple bugs in this part of the code, and so this removal is really going to be a huge kind of weight off the shoulders of client implementations. So I'm personally really excited about the pending validator set removal, and hopefully it'll tie really well into a future ACP around continuous staking. But yeah, as far as like the UX goes, it doesn't really change it too much. The only difference is that when you issue a transaction or a validator or delegator transaction now, it goes into effect immediately. So the start time is essentially ignored in the transaction. So for the most part, this doesn't really change much UX, except for, perhaps it's starting slightly earlier than would have previously been expected. So this is really just kind of a huge weight off of client implementations. So yeah. And then I think the last one that we want to talk about on the P chain is the sorry, what was the last one on the P chain? Oh, the disabling of the legacy add validator and add delegator transactions. So this is going to do two things. So first of all, these transactions are completely kind of replaced already by the add permissionless validator and add permissionless delegator transactions. So these were just strictly duplicate functionalities. And what it also does is it is going to significantly increase the BLS adoption rate across the network. So we saw really a kind of I want to say, I don't want to say disappointingly slow, but like very slow adoption of BLS keys, primarily because like large kind of staking solutions just kind of didn't change their code and kept using these legacy transactions for longer than probably expected. And the reason that maybe there wasn't a huge desire was because kind of warp messaging didn't come out, and warp messaging is kind of the primary use case, at least currently, for these BLS keys. But now that warp is out, the more validators that adopt BLS keys, the more that we'll be able to participate in cross subnet messaging. And also, as these BLS keys are adopted throughout the validator set, we can unlock kind of future optimizations and future ideas. So this is kind of biting the bullet and removing this long deprecated couple of transactions, and I think it's going to really further unlock the kind of potential of our BLS key registries on the P chain. So
yeah, some ideas there are first of all, like revamping the performance of the P chain voting mechanism to make it a lot more scalable. So instead of using proposal blocks, use like BLS signatures for voting of uptime. Subnet attestation. So like one thing that would be really cool is to like actually sign the accepted frontier of the primary network on some like regular cadence, so that non-validators don't actually have to run consensus, and that they can just like accept the output of the consensus. But also, if you're not connected to a particular chain, you can use that information to prove data about like blocks and the contents of them, which is super useful for subnet only validators. And then it's really easy then, the whole class of algorithms of subnets as a whole sending something to the primary network. So that can be verified. So this would be something along the lines of like, hey, like mint someone some tokens, or like, hey, change my staking parameters, or hey, whatever. You basically turn subnets into these like governable agents that the VMs on subnets then can determine like whatever can trigger those sorts of standard actions.
So I actually see in the chat, like, when can we get Avalanche Lite clients? So this is actually something that could potentially unlock running an Avalanche Lite client, because if we were, if we had a sufficient adoption of these BLS keys, then we could actually use these inside of consensus to perform what are called client certificates. So basically like certificates of acceptance, which Lite clients are then able to follow. So that's actually kind of a huge unlock here over time. So
yeah, the alternative to that would be, your little Lite client opening up like a couple thousand connections to like different validators on the network. And so like not really feasible for most mobile phones, and especially in some jurisdictions. So but you can think of like subnet validators in the same way, right? Like you don't want them to have all that extra burden as well. So like you should try to also minimize their footprint. So you could have like this hyper minimal footprint where they don't even sync the P chain fully. They just use Lite clients everywhere. So they don't even have the P chain state, or like the previous P chain states, I guess. That gets weird for the whole registry tracking and everything. We can get into that a different time, but this is the gist of what it could unlock. So this is a change in there's some feedback we also got was that Avalanche JS doesn't support this yet. So there's a V4 hopefully coming for Avalanche JS in the next day or so. That's a full rebuild of Avalanche JS, and hopefully, makes it a lot easier to interact with the Avalanche network, including all these new transaction types. So that's what
V2, or did we skip a couple?
So Avalanche JS is on the public repo V3. We called the rebuild V2, but when it's integrated into the Avalanche JS repository, it'll be V4.
See, that was the first time I heard that.
You gotta get with it, Aaron. Yeah. There's one last one before we get to the warp stuff, which is virtual machine application errors. I think this is the wrong link. I may have linked it wrong. Yep. The blog's wrong. Got to fix that. All right. Virtual machine application errors.
Unless people are tired of my voice, I guess I'll keep. So the app errors. So this was proposed by Josh. So essentially, this is probably the start of a longer push of ensuring that we have every message actually has a response. So currently, if you send a app request, so an app message, so all the things prefixed with app over the P2P network are VM specific. If we send a VM specific request, for example, like a mempool, like, do you have any new transactions request to another node? If they, for whatever reason, they aren't able to support that request, or there's like some error, what'll happen is they basically just drop the request and say like, that was weird, don't know how to deal with that, drop it. And that requires the client or the person sending the request to essentially hit a timeout. And it doesn't really give any information as to what happened, like why the request failed or anything like that. So going forward, we're hoping to basically send these app errors back in every case, so then the client can get that information both faster because they don't have to hit a timeout, but also including the actual issue that caused the request to fail. So this is actually specifically for like supporting handling. I believe that's kind of the case here, but sending should be activated in probably a release or so after after Durango is activated. Yeah.
Yep. I think this one is also useful for like networks that want to have, let's say, we'll call it like more advanced data replication outside of the block. So what typically would happen in this case is like you are missing some data and you want to like for some reason go get that from other peers on the network. Right now, the only way that that's done, that's you can do it is two ways. One, you can wait for the timeout and wait for the request fail to come back in, or you can send a successful response that says not found or like some sort of error condition that you can handle, which is really confusing as a application developer in that way. And so having the ability to like instead properly segment errors out of the successful response type can just make handling a lot clearer, in my opinion. All right. Now for the fun part, if that wasn't already riveting enough for you. So Stephen pulled the data up of like in Avalanche Go alone, there were 110,000 line additions and 81,000 deletions since V110. I don't know what that looks like in Core ETH, but a lot has come in and out of the code base in this release cycle. So one of the biggest things that is in this, and one of the biggest things that I think we've ever really implemented end to end is warp support particularly with support for the EVM and on the C chain in particular. So with that, we have ACP3. So Aaron, take us away.
So Stephen, when was the first Avalanche Warp message sent? Was that December 2022?
Yeah, December 2022.
So in December 2022, XSVM, the OG VM.
It is UTXO based. Yeah.
The OG UTXO cross-chain VM on Avalanche was used in order to send the very first cross-chain message on the Avalanche network. But since then, we've done a huge amount of work in order to integrate that exact protocol into the EVM. So why would we do this? Because XSVM was only a toy example in order to show how the low-level protocol would work, in order to show how subnet validators could use the P-chain registry, the P-chain as a registry of subnet validator sets in order to dictate who should be signing a message and how recipient subnet can verify a signature from there. The XSVM is actually account-based. Too bad. And the big motivation for integrating into the EVM is that this is what people are typically using. And so a huge amount of work has gone into actually bringing Avalanche Warp Messaging to the EVM. And as Patrick mentioned earlier, the way that we typically add extensions into the EVM is through precompiles. And so the way that people will interact with Avalanche Warp Messaging via the EVM is the precompile Solidity interface that's defined here. The really nice thing about extending the EVM via precompiles is that it doesn't require any changes whatsoever to the Solidity compiler. Instead, all that you have to do is know what the address of that precompile is, and then you can interact with it in the exact same way that you would with any other smart contract. So using this interface, there are two payload types that we've defined that the EVM can interact with. One of them is a warp message, which contains a source chain ID, the sender address, and some arbitrary byte payload that's defined as you can see there. And the other one is a warp block hash. And so this is a source chain ID and then as well as the block hash. And so these are the two message types that you can use in order to essentially say, I want to verify that this warp block hash was signed by the validator set of subnet A that sent some message, or that this warp message was in fact sent by a specific sender address on that source chain. And so with this protocol was designed in order to offer a very low level primitive in order to build on top of. So you'll see this is probably a little bit short of what you would actually want to use as an application level developer. If you wanted to build something like a cross-chain application, you probably don't only want to have an origin sender address, but an origin sender address and then also a destination address to call. And so what we did here was we offered the lowest level protocol possible of what exactly actually needs to be verified by the VM, so that anybody that wants to can build an additional interface on top. So because we have this arbitrary byte payload, I think Michael was actually the one that pointed out a while back that when we were making some changes to this interface, we realized we actually didn't really even need the destination address if we were going to be building additional intermediate protocols on top of it. And so all that we actually have here is this source chain ID and sender address and payload, and you can build whatever else that you might want on top of it. So this doesn't provide anything along the lines of ordered message delivery, nonces, delivery only once. And instead, all of that is sort of delegated to protocols that want to build on top, basically noting that the only thing we really need to provide here is some sort of authentication. And from there, we can add on all of the additional mechanics that we might want. And so I think Michael can talk a lot more about how Teleporter was built in order to take advantage of that, in order to build the first example of an application level SDK so that people can actually build their smart contracts in order to leverage Warp from the ground up.
Yep. It's a great handoff point. Pick up right where Aaron left off as far as diving into what that payload is, which is relatively opaque at the VM layer, I would say, such that contracts get to define it. So Teleporter takes enabling Warp within the EVM one step further to make it as easy as possible for smart contracts to invoke each other across EVM chains within Avalanche subnets. And it provides the replay protection that Aaron was mentioning isn't provided by Warp. It provides incentives for actually relaying the messages from one chain to another, since there's a source chain transaction, which then needs to be the message within that transaction needs to be provided with an aggregate signature in order to send on the destination, and also so you incentivize a relayer to perform that aggregation and delivery. And then it also provides a really nice interface for just being able to call send cross-chain message, specify your destination, since that's not specified within the Warp message, as Aaron was pointing out, and not worry about any of the verification of the message, the actual signature aggregation, or anything like that under the hood. So Teleporter is something that we've been working on for just about as long as we have been working on Warp. It's taken many different twists and turns along the way, but we're super excited that it's now live on Fuji. And so the step after that was, okay, great, Teleporter's out. Now what can you build on top of it? Which is an open-ended question, of course. You can really build anything on top of arbitrary messaging protocols. But as one such example, we put together an example use case of using a VRF, verified randomness function, from another chain on your Avalanche subnet EVM instance, and just put out a short Twitter thread that highlights the power of using Teleporter for this use case. But like I said, it's really just one possible use case. So yeah, excited to get it out the door and to have people start using it.
Yeah, this one Michael whipped up on the side, told me about it last night, and I was like, all right, yeah, cool. I guess you could do that. That's sick. So like, I think one thing that he comments well in the thread where he shared this post is that the whole point, like the massive benefit of having Teleporter and Warp here is that you can utilize the functionality of other chains that have different state or have previous implementations that exist without having to have access to it all the time. That's the big trade-off you're making by like having a subnet that's not, one massive composable state with everything else. But it turns out that a lot of times you don't really need to have full composability all the time. And so if you believe that that is the case, then like teleporter and warp can be very nice. Like, maybe, for example, you have some USDC balance on the C chain and you want to bring that into your subnet. And then on your subnet, maybe you control the gas fees, or maybe the gas fees are paid in USDC, or, whatever. Long story short, you can get very different properties that then or very low fees. And then at some point, if you want to interact with other things, maybe there's stuff to play on the subnet, but you can always bring it back to have a broader interaction. Now, it's interesting when you then take that one step further and say, what if the chain is a consumer of different things that are on the primary network or on other subnets? Because the chain is the one that really sends these requests out. So you could say, hey, I'm the chain, give me some VRF result that I then include at some point in time. Now, there's nuance to this, which I think Luigi commented when I was talking to him, is that if you can front run the message getting to your subnet, that's not going to work, right? So typically on the subnet, the game or the input has to be committed to before you go request the VRF result. But you can at least know that once the request is submitted for the VRF result, that it will be provided to you safely. And that's the real key. So it's not a perfect atomic solution, but in terms of being able to use integrations from all over the place without actually having to, integrate a VRF on every single subnet if one's not natively provided, can be really nice.
Yeah, the whole shift of having services available on one chain be used by other chains, I think is a kind of huge paradigm change from your typical EVM chain, which you need all of the applications within the same chain for them to be able to, their contracts be able to call each other. If you could just have price feeds be their one own independent subnet and consume the current value whenever you'd like to on your own subnet, then it's a whole different world.
So yeah, the fun part we'll get to do is take the HyperSDK and hook that up to this to somehow get messages running on the C chain. But I think one thing that we also decided to do is, there are obviously infinite examples and tweaks you could make here. But we selected what we felt like were the most common use cases. So in particular, the first one being token transfers from the C chain to the subnet and back. So ERC20 or native Avalanche, and getting that example audited, hopefully for use by the broader ecosystem, because we feel like that will be a very commonly used one. But, as soon as you venture off the standard path of I want to transfer some crazy thing or call some actions, we don't plan to maintain an audited library of every possible interaction, but we'll hopefully, help cover some of the audit expense for getting some standard template out the door. So in particular, the first one of those will be the ERC20 / native token transfer example. So you could have a token defined on the C chain and then use that token as the native token in your subnet. So yeah, I think that's the gist. Anything else you guys want to add to the teleporter side or warp side?
Excited to see it on mainnet.
Yeah.
So I think
excited to see it on testnet for now. Excited of the possibility of seeing it on mainnet in the future.
So we had the teleporter demo that was running on Fuji for a while, right? That was updated now, right, to point directly and use the Fuji C chain. Correct me if I'm wrong.
Yeah, so we had 3 subnets that were teleporter enabled amongst each other before Durango activated. Those were Amplify, Bulletin, and Conduit. They were used by Oh My Warp. We played around with that demo. Since then, we've made some further breaking changes. And so now we are moving on from Amplify, Bulletin, and Conduit onto 2 new testnet subnets called Dispatch and Echo. So we will soon update Oh My Warp to have the same demo of bridging ERC20s between those two subnets and the Fuji C chain now. Now that Durango is active.
Yeah, and then the cool thing there too is we already have faucets up, so you can get tokens on either Dispatch or Echo to start playing around with sending messages to the C chain. And then Glacier, which is like the API that powers Core and all the explorers, will index teleporter messages as well, so you can query those using Glacier too. So that'll be a nice little feature that will power Oh My Warp behind the scenes.
Yeah, so if there's any developers that really want to test around and play with Teleporter prior to the mainnet activation, this is kind of its final form. So we're not expecting any kind of other changes. So playing around with those testnet subnets and the Fuji C chain should be a really good kind of feedback mechanism for if there's any say like UX suggestions around Teleporter or things like that. Of course, if if there's suggestions around C chain warp, the ship might have sailed a little bit at this point, but but if there's any last second suggestions, we're always of course looking for feedback. So
there are some there was a lot of thought put into the upgrade strategy around the teleporter contracts. I highly recommend you check that out too if you're curious what happens if there's a bug or if there's something that should be updated. It's a very interesting and unique, I think, approach to upgrading the on-chain logic. Obviously, if there's a bug in the precompile, that's a different issue. But in the case that there's a bug in Teleporter itself, there is like some interesting thought put into the upgrade strategy there. So I see one question on this: how do you compare Teleporter with IBC or ZK LBC? I'm not sure what that one is on performance.
it's probably ZK IBC, I guess. Capital I.
Yeah, possible. Good question. I think we've covered this a number of times in different things, but to reiterate, I think warp messaging just takes a different approach at a higher level than what IBC takes. So IBC in general relies on point-to-point connections between zones that have channels. And to keep those channels functioning, you have to keep passing updated validator sets and state roots that can be used to prove that messages were included in the state and signed by some percentage of that validator set. Which is interesting, and that the chains don't actually execute the state transitions of the zone that they're connected to, which is similar to what we do. But the difference is with us is on the P chain serves as this registry of which messages should be validated and who can actually validate them, and so there is no per connection variable cost to actually communicate between two subnets. The downside is obviously that you now have this other chain that everyone is connected to, but in a world where you expect there to be a lot of messages and you expect those messages to go every which way, it's just a very different model where you don't have to do point to point to point connections over some path to get somewhere. You should assume that every subnet is probably going to be connected to every other subnet or much closer to that idea. Obviously that's up to the subnets to decide if they want to accept messages from any other particular subnet.
Yeah, specifically the way I think about it is that rather than running essentially a light client for all of the chains that you're trying to communicate with, you are running the P chain. So that's kind of the major difference between IBC and warp messaging at its kind of core. Also, as you mentioned, I think IBC is a little bit of a higher level messaging format than warp, but yeah.
Yeah, I think
Oh, sorry, go ahead.
I don't want to interrupt the Mr. B's question.
No, you go.
Yeah, before we get to the Mr. B's question, the other important thing to clarify, because I think a couple of people have asked us this a number of times, is it's very important to note when warp messages are being exchanged between subnet A and subnet B, when we talk about the P chain being involved, we're only talking about using the P chain in order to read the validator set of the source subnet at the time that message is being verified, but messages are not being sent to the P chain and then delivered to the destination chain, which would incur an additional cost to make the P chain a potential hotspot and for the entire network and for the entire protocol. We explicitly don't do that, so that the P chain actually has an extremely low write overhead. There's a very, very low write load on the P chain. And so all that we have to do is to make the P chain sufficient for everybody in the network in order to be able to use it to support Warp is to make it have very high read capacity. So as long as it can only needs to support the write capacity of all of the updates to validator sets throughout the subnet, which we sort of expect to be relatively slow as these updates aren't happening overly frequently. And then in order to handle the read latency, it's not even all the validators of the P chain that have to perform those reads. It's explicitly each validator that is verifying some warp message to a subnet that they care about, that they then have to use the P chain in order to read the validator set there. So it's a really nice design in that it doesn't create this hotspot from the P chain, but still has this sort of hub model to a hub and spoke system. Whereas on Cosmos, you might have each of those point-to-point connections are involved on both sides of the connection. And I think actually a better comparison might be Polkadot, because I think their original cross-chain communication paradigm had them going via some main chain in order to route the message to its destination. So this explicitly avoids that design in order to reduce that potential hotspot. And the other thing I was going to say, and then I'll let it get to the Mr. Beast question, was in comparison to IBC, it's very much intended as a lightweight protocol design for people to build protocols on top of. So there's a very clear separation in Warp and Teleporter between the low-level protocol and then the higher-level application protocol that applications might want to deal with. But it still leaves a huge amount of room for potential application developers or other potential developers that want to build an alternative to Teleporter and provide potentially slightly different properties. If they wanted something like totally ordered message delivery, or if they wanted to just skip some aspects, or they wanted to have a slightly different SDK, or if they wanted a different fee incentive model. It's totally open for people to build on top. So I think of it as more of a Lego building blocks, whereas IBC is sort of this complete solution. We still, at the end of the day, for any application developers that want to use it, they can use the complete solution because the combination of Warp and Teleport already brings it to you, but it's a bit more of a pluggable model.
Yeah, no, that's a great thing to point out, because it is a big point of confusion where people think that the P chain is going to kind of be the bottleneck for Warp, but it's actually completely not used during an actual communication between two subnets. It's only used for reading, which is free, essentially. Yeah, so the Mr. Beast question: when will VRIX come to the C chain? So I want to touch on this a little bit first, and then Mr. Beast himself can jump in.
Not with I don't have a view anymore. I don't know if you guys...
Just so everyone watching knows, we do call him Mr. Beast internally as well now.
It's
yes.
Yes. It's taking over like wildfire. So
great work.
So in my kind of opinion, and Patrick can comment on this as well, so decoupled state machine replication is really a mechanism for avoiding kind of a bandwidth bottleneck on the block producer, the block proposer. And that is something that comes up when you have kind of very large blocks. So like if you have you're using a lot of bandwidth and you have to kind of send them to as many people as possible, and gossip is going to take maybe too long or be like not resilient enough. So that isn't really a problem on the C chain at this point. The reason the C chain isn't able to progress at speeds similar to those of like the Hyper SDK or things like that is because one, it's kind of not parallelized, and specifically what I mean by that is that the way that the C chain currently works is you'll be executing a transaction and then you'll perform some DB read, and the whole execution will halt as that DB read is being kind of like fetched and then brought in, and then disk is really this kind of like major latency increase during the actual execution of the EVM. So if you actually had all of the state already provided, the EVM would actually execute relatively quickly. Once you get past that, you can actually maybe parallelize the actual execution of transactions even more, so you have multiple transactions happening concurrently. But really the issue is that you're not able to fetch data from disk concurrently. So one of the things that the Hyper SDK did very early on is it specified the state keys that it was touching so it could fetch all of that data from disk very rapidly. So on the C chain, I would say that there's a number of bottlenecks that need to be hit or gotten over prior to looking for decoupled state machine replication to improve the performance. And then VRIX is kind of a way to protect a decoupled state machine from various client level DOS vectors. So I wouldn't look at VRIX as this like shining bullet to like improve the C chain, but it's very much something that if a VM is designed to be extremely high performance, then you will end up hitting this kind of bandwidth bottleneck. And in order to get over that bandwidth bottleneck, you need to decouple the kind of transaction propagation from the actual block production. And then once you do that, you need to make sure that it's still DOS resilient. So that's kind of where VRIX is. Like VRIX is kind of the third or fourth step deep into the high performance VM world. And so I wouldn't necessarily look at it as something that is immediately applicable to the C chain. There is still a lot of things that we want to do to improve the performance of the C chain, but that's not necessarily directly something that's fully applicable. So at least right now. So I don't know, Patrick, how much of that you agree with, but
I think there's one nuance that I'm not sure I fully agree with, which is around like the main usefulness of decoupled state machine replication is just to help better like utilize the bandwidth. There's one other aspect of it, which is the part in which state is accessible and verifiable during both the building and verification part. So like, I guess like when you're building, you typically need to wait to fully verify the parent to produce the next block. With decoupled state machine replication, that's typically not a part of it. And that has nothing to do with like bandwidth utilization. It just has to do with, now the thing I'll say is typically optimization is the death of UX if you're not careful. Because like, you can add like 15 fields you have to specify to issue a transaction, and like it may be super optimal on chain if it's executed, but like the users hate it. So the hope with VRIX is instead to better abstract the EVM state transition function in the short term, and then add that as an action support within the Hyper SDK. See how that goes, rather than trying to build the entire like core ETH system around VRIX, which would be like, to say a full rewrite would be an understatement probably. Like it is deeply changing a lot. And so it's definitely easier to instead treat like this EVM state transition function as an action. And then if that happens and that goes well, then I think there's very interesting and contentious questions to ask about where things go from there. So that's what I would say. But until we get to that point, I think it's cart in front of the horse a bit. But like, we get, if you do that just state transition function within the EVM, you get, smart contract support out of the box on the Hyper SDK. The EVM state transition function is actually not bad. It's just that part is not usually where most of the latency is. It's just that the whole thing is very intertwined and built around very strict assumptions that make it very difficult to modify in place. But so once it's on the Hyper SDK out of the box, it gets like all this database stuff we've been doing. It gets like the decoupled state machine replication. It gets multi-dimensional fees. It gets like custom auth. Like there's a lot of really nice things you get just by doing that. So we're going to start there and see what happens. But if that goes well, like could be pretty cool. I think that's probably a good ending point. I think we're at time anyways. So thank you for everybody tuning in, and we'll see you next time. I think we have next week, there's a Hyper SDK dev community call, actually, which is like going to be a different format. So it's going to be a Google Meet, and then you can live stream the Google Meet. So we're going to have a bunch of people in there that are building on the Hyper SDK, and we're just going to kind of talk about things that are going well, not going well, feature expectations, stuff like that. So it should be a fun conversation. We'll see how that format goes. Maybe something we can consider bringing here. All right. Thanks, everybody. See you.
Thanks, everybody.